Well, welcome. Today is Wednesday, November the 18th. Wow. Countdown is 9 days until I get married, just FYI. Yes.
You're doing the thing.
Getting married on Black Friday. It's, I thought I'm getting the best deal in town. So, but that is irrelevant to AP Chemistry. But it makes me in a good mood. So, today we're going to start talking about gas laws. And I want to begin by discussing what pressure is. Okay, so I have a balloon. So what's causing pressure in this balloon?
Number of atoms in X amount of space.
The number of atoms in X amount of space, that's going to affect the pressure. Okay? But what's actually causing the pressure? What caused that balloon to expand? The air. Okay, but well, we need to be on a smaller, let's get a little bit more deep. Let's get deeper. What about the air? What's the air doing? Hitting the walls of the balloon. Pressure is caused by collisions of gas molecules with a container wall. With the container wall. So, how do you think we increase pressure?
Putting atoms in there.
Okay? Pressure can be increased by one, what did you just say? Decreasing volume, or what did you say?
Adding more electric,
Adding more gases, right? So both of those do what? But decrease the volume or add more gas, what do they change? I heard the concentration. I heard somebody mumble it. Okay? So we can, number one, increase the concentration. More gas molecules. So there are two ways in which we do that. We already mentioned them. Okay? Decrease the volume. Or add more gas. Okay? What's another way we can increase the pressure?
Increase temperature.
We can increase the temperature. Okay, we can increase the temperature. What does that do? Okay, so molecules move faster. So what does that do with the number of collisions? I'm just going to abbreviate equals more collisions. More collisions means more pressure. Increase the concentration, more collisions, more pressure. Okay? What else does increasing the temperature do? Heat them up.
Increases the energy of the collisions.
Okay? Because if you heat them up, what do you do to their speed? Increase. Heat them up, speed them up, right? So when they hit the container wall, what'd you say, Amy?
It would increase the energy of the collisions.
It's going to increase the energy, okay, of the collision. Okay? Gases collide with walls more energetically. Okay, so pressure is just caused by collisions of the gas molecule with the container wall. So we can always change the pressure by changing the number of collisions. We do that either by changing the concentration, which can be done by either pushing it into a smaller volume, which is what you do with like a bicycle pump. You push that piston down, you have a certain amount of gas in the piston, you push it down, you're decreasing the volume, which in effect increases the concentration, increases collisions of the gas with the sides of the pump, and it increases the pressure. But the reason you're doing that is to put air into a tire, so you're adding more gas into the tire, which also then increases the concentration, increases the pressure. Now, as it's getting cold outside, you might have in your car, your tire pressure get light and might come on. That doesn't necessarily mean you have a flat. What's happening? The decrease in temperature is causing molecules to move more slowly, the pressure to drop. So you got to put more air in your tire in the wintertime when it's cold than you do in the summertime when it gets hot. Most of the time, when you're looking and it tells you what pressure to put in your car tire, it says cold tire pressure, because it's, in other words, before you start driving, it's supposed to be, most of them say 32 PSI. Because once you start driving, the friction causes the tire to heat up, causes the pressure to heat up, generally about 3 PSI, pounds per square inch, just as the friction increasing the temperature of the gas in the tire. All right, so how do we measure pressure? Pressure is measured in, what are some of the units pressure is measured in?
Atmospheres.
Atmospheres. 1 atmosphere is equal to, I didn't hear that, what?
Pascal.
Pascals, how many pascals?
220?
No. 101.3 kilopascals. Okay? And this is the actual SI unit, but we never use it. Okay, SI, Standard International System, that's your metric system. Anytime you see SI, that's metric. Okay? So that's the actual metric unit of pressure, because that's going to be newtons per meter squared. Okay, the force is newton, which is like pounds, meter squared like pounds per square inch. Okay? What would that be in PSI? Anybody know what the pressure is on you right now in PSI? Nobody knows, really? Just too much, right? Too much pressure, especially this week when you have a test in every class this week. At least I gave mine on Tuesday early on rather than at the end. So
I prefer
you prefer the end and just cram it all and just have 2 miserable days? All right, 14.7 pounds per square inch, which we call PSI. What does that mean? That means the atmosphere right now, the weight of the atmosphere, the oxygen and nitrogen and argon and all the things in the atmosphere, there's 50 to 100 miles of air above us, and the weight of that is pushing on every square inch of your body with 14.7 pounds. Okay? Now we're designed to handle that. Our bodies actually, if you go into space, okay, I don't know if anybody has ever seen the original Arnold Schwarzenegger Total Recall. Okay, they have a big battle out in space, but a guy goes and he gets thrown out into space, but everything blows up. Your eyeballs, just all the blood vessels in your eyeballs burst. You bleed out of the ears and everything. All your blood vessels just burst almost instantly because your blood vessels are like a balloon. Do that every time. Every time your heart beats, they expand, they contract, they expand, they contract. But the atmospheric pressure is pushing on them to keep them from expanding. But if the atmospheric pressure is not there, they just expand way more, and as a result, they burst. Matter of fact, let's just look at that. Let me just burst your bubble here a little bit. I have here is a vacuum pump. A little bigger, a little bigger.
Something she actually did. That makes sense. Yeah. Then she messed it up. I don't know. I can't remember. I just remember when we made ice cream. Yeah, I did ice cream. And JP like spilled it all over.
Well, we'll see. Probably when we come back from Thanksgiving, we'll make ice cream in here as well, but we're gonna do it with liquid nitrogen rather than.
Oh yeah. Oh, so we're doing the manly version. Remember when we made the Kool-Aid?
All right, so what is the definition of a vacuum? Boy, I'm really up close and tight here. Okay, but I'm not within 6 feet of anybody, just for anybody watching here. Therefore, I don't have my mask on because I have to keep blowing these balloons up. But what happens in it? What does a vacuum do? What does it mean to vacuum? Okay, so this thing really sucks, right? Okay. Happy Wednesday. Okay, so it's going to suck all the air out. So what's that going to do to the pressure inside of there is a technical difficulty. I thought that because it had this little lip on it that it wouldn't suck down onto it, okay? And what caused this to break? With pressure. Okay? It was actually okay, let's try this again. So what happened is all the air got sucked out of this, and this was stuck down onto it, but it wasn't allowing the air to get sucked out of here. Okay? But again, I thought it wouldn't make an airtight seal because it had that little port spout on it, which I'm counting on the same thing happening here. There we go. So as I'm decreasing the pressure, why is the balloon expanding? Why is the balloon expanding? Okay, say that. I mean, you got to speak up.
There's nothing keeping the air inside the balloon compact anymore.
Okay, those of you that have physics or engineering, vectors. Okay, outward force and inward force. If there's no motion of the balloon, that means the pressure on the inside is the same as the pressure on the outside. So as I decrease the pressure on the on the outside, suck the air out, the balloon then doesn't have as much resisting it. So it expands more. Until, and as it expands, what happens to the concentration of the gas molecules? Does the concentration increase or decrease? Decreases, right? So as a result, what happens to the pressure? It decreases. So as it's expanding, it's decreasing to where the pressure inside is equaling the pressure outside. That's what happens inside of your blood vessels in your body. You have a pressure inside your blood vessels. The heart beats, you got going and expand and contract, but the atmosphere is keeping them from expanding, is resisting that, just like the atmosphere is resisting this. But you take that atmospheric pressure off in space, then all of those gases inside have nothing resisting it, and they expand like the balloon expands, and as a result, They break. Have you ever heard about, like a football stadium, you're in the nosebleed section? Why do they call it that?
Because you're so high.
Because you're up so high, what happens to the pressure when you go up so high?
Decreases.
It decreases. So the little tiny capillaries in your nose, okay, that they're the most vulnerable capillaries, which is why you do cocaine. Well, hopefully not you do cocaine, but it's why people do cocaine, all right, is because it just gets absorbed in those tiny little blood vessels in the nose and gets in the body super fast, okay? But they're very sensitive, and so when you go up high in altitude, there's less air pressure, so when your heart beats and those expand, you don't have the pressure to help hold them and keep them from bursting. If I had a little tiny balloon, I could make the balloon burst. We saw the cup burst, okay? So, I really needed that, but, so, I really kind of busted right on my finger too, but anyway. So your blood vessels in your nose are the first ones to break, to burst with the lower pressure, and so we get nosebleeds. Technically not the top of Bryant-Denny Stadium, but if you go up into the mountains to go skiing, a lot of times people that go skiing get nosebleeds because the pressure is so much lower. Okay? So, 14.7 psi. We can see this more dramatically. Let's let the pressure back in. Okay, now, by the way, if I try to get this off right here, I can't do it. Because there's 14.7 pounds on every square inch. So if I go and I measured how many square inches this glass sphere has, that's the total weight that's being pushed down, pushing that onto this. There's really no such thing as suction. It's just unbalanced force, unbalanced weight of the atmosphere, and there's nothing pushing back out. When you go and put a suction cup, like I have my radar detector on my car windshield with a suction, okay? And so, what's actually holding that radar detector on my windshield? The pressure differential. What's the pressure on the inside of the suction cup? Less than 1, very low, because you push all the air out. Okay? So it's really the pressure of the atmosphere pushing against that suction, and so you look at how many square inches, there's about probably at least 2 square inches on that suction cup, which means there's going to be 29.4 pounds pushing against that, and the radar detector doesn't weigh anything near that. And so it'll hold up as long as there's a good seal and air can't get in. Now the minute that I let air in, so now the pressure increased, so now they push back down on the balloon, and now I can get this right off. Because now the gas is pushing out with the same force as the air pushing in, and so the only thing I have to overcome now is the gravity, the weight of the jar. This is called a bell jar. Alright? So, anytime you have a suction like on a little hook on a window or whatever, it's really not suction, it's not being sucked in, it's just the weight of the atmosphere pushing against it. If I take a Mountain Dew can, put a little bit of water in it, heat that water up. That's heating up. I just have a pan. It's going to have some ice water in it. Alright, so we got to wait till we see steam coming out. So if a steam's coming out, what does that mean as far as water vapor in the can and all that? What's going to be the pressure inside the can with the water vapor? I didn't hear anything. What?
It's going to be the same as the vapor pressure.
The same, well, not the same as the vapor pressure, the same as atmospheric pressure. Okay? because it's open at the top, so the pressure inside, so the gas is going to continue to expand, but as the pressure would build, it's going to come out the top, and pressure always wants to kind of equalize itself out. A watched pot never boils. I'm going to put a little bit in there. It should start boiling pretty quickly. I see heat all around the outside of the can. Does anybody know what I'm going to do?
Pick up pressure.
Huh?
Pick up the can.
I'm going to pick up the can.
Put it into the
If I
ice.
put it into that,
It's gonna like crush.
Yeah.
I don't want to be impatient because it'll ruin the moment. I don't see it coming out, but I think it is. All right, so we have, the can is full of water vapor right now. But what happens when I put it into cold water? What happens to that water vapor? It condenses back, so if it's underwater, no air can get back in, so as that steam condenses, what happens to the pressure on the inside? It decreases. Right now, the pressure inside and outside are the same, so the can doesn't collapse. But if I take this and I turn it quickly underneath, just make it not quite so hot. Okay? The can crushes. I need to leave it on there so it crushes a little bit more. But what caused it to cave in? What caused it to cave in? The difference in pressure, okay? Because once we turned it upside down in the water, then the steam condensed. And we're going to try it again. It can be a little bit more dramatic than that. So we'll just let this go a little bit longer, okay? Now, so pressure, what are some other units of pressure? Millimeters of mercury. Which, just so you know, another name of that is a torr, named after Torricelli, the guy who invented the barometer. Gotta be kidding me. No, I don't. I'll be right back. Somebody locked the door. So here's a big test tube. I take some water. I really see the steam coming out now. Okay, let's watch this one. Okay, you ready? Here we go. All right. Big time collapse. As soon as we put it in there. And it sucked all the water up into there as a vacuum. Okay? So again, what caused it to collapse? The pressure of the atmosphere being unbalanced. There's no pressure on the inside, nearly a vacuum on the inside as the steam condenses and goes back to water. And so we end up having the can crush. That happens sometimes if you leave a gas can out in the sun in the summer, and you put the cap on it tightly and then put it in your garage where it cools off at night. Because as it cools, the gas condenses back from vapor, and then the atmospheric pressure causes the can to kind of cave in. All right. We're going to show you some more magic. I don't know if I'm going to have time to get to all these. That's all right. So I'm going to take this big test tube. It's actually a gas collecting tube. Fill it up with water to the tippy top. I'm filling it up with water. You guys can't see it, but I'm just filling it up with water.
Are you filling up water?
Okay, so you can kind of see the little crest meniscus across the top. I put my thumb over it, turn it upside down, and put it under the water, and somehow, some way, the water doesn't come out of the tube. How, what is keeping the water? How come gravity isn't working on this one?
Pressure.
I bet it has something to do with pressure.
Pressure on the surface of the water is pushing all the water back up in the tube.
Okay, the pressure of the atmosphere on here pushing the water up in here. Now, let's just clarify. If this water comes out, what's going to happen to this level of water inside? It's going to go up. But the atmosphere is pushing down with 14.7 pounds on every square inch. Therefore, this doesn't weigh 14.7 pounds. That's not putting the same amount of pressure down. So it's supporting the column of water. Okay? Anybody know how tall of a test tube I have to have before the water weighs, puts a pressure of 14.7 pounds per square inch? Does anybody scuba dive? No? Every 33 and some change, every about 33 feet is 1 atmosphere of pressure for the water. So I would have to have a test tube over 33, 35 feet tall. That's like from the window here down to the ground. Fill it up with water, turn my thumb over it, and then the water level would drop until the pressure, the weight of the water equaled the pressure of the atmosphere pushing on the surface. In essence, I just created a barometer. But a 35-foot barometer is not very convenient, so what do we use? Mercury. Mercury is 13.55, 13.6 times more dense than water is. So to get a column of mercury to be supported by the atmosphere, 33 feet divided by 13.6 changed into millimeters is 760 millimeters, which is this tall. So I have a glass tube, little over this tall, at the barometer factory. They fill it full of mercury, put their thumb over it, turn it upside down into a bowl of mercury, and then we have a column supported by the atmosphere. A high pressure system comes through, it pushes down more on the surface of the water, forcing the liquid up higher. A low pressure system comes through, less pressure pushing on the surface of the liquid level rises up, this rock comes down some, and so the mercury rises up and down. We are the only country in the world that doesn't measure pressure in terms of millimeters of mercury. We measure it in terms of inches, 29.92 inches of mercury. So when we see barometric pressure, like right now it's probably 30 point, oh, I don't have my phone. Hey, does anybody have their phone? Pull it. Hey Siri, what's barometric pressure in Birmingham, Alabama?
Hey Siri, what's the barometric pressure in Birmingham, Alabama?
The barometric pressure is currently 30.56 inches of mercury.
30 point what?
30.56.
30.56. So we have a high pressure. We have more than 760. We have more than what we would call 1 atmosphere of pressure right now. Okay? because I knew because it's clear and it's dry, so that's usually a high pressure. Storms is low pressure. And so 30.56, we're measuring it in inches. Every other place in the world, including everything we do in science, is going to be the equivalent of millimeters of mercury. All right? But it's how much column, how much will the atmosphere support? So we measure, okay, atmospheric pressure is measured with a barometer. Well, what if I want to measure the vapor pressure of a liquid? Okay? Here's some alcohol, C2H5OH, ethanol. Okay, so here's my ethanol. I have a little valve right here that can stop the vapor molecules from coming. This is mercury in the original U-tube, okay? So this is a U-tube full of mercury. Because gravity is going to pull equally, they're going to be at equal levels. But this is a vacuum up here. So what does that mean? What's above this mercury right here? What does that mean, vacuum?
No.
Nothing. Okay? It's void. Now that's a weird concept to try to really deal with. How can there be nothing? There's got to be something. But a vacuum means nothing. So there's nothing resisting pushing down on the surface of this mercury at all. But gravity's pulling it down, gravity's pulling it down. So we begin heating this up, or we just let it go and it's going to vaporize. And we open this up and let it vaporize through. So what's that going to do on the surface of that liquid? It's going to push down, right? What's that going to do here? Push up. So then we're going to end up having this down here and this up here. And so this distance right here is going to be the millimeters of mercury that this vapor is supporting. So we're going to measure the vapor pressure of our liquid using what's called a manometer, a manometer. Some might think that's a group of girls at the mall, just kind of checking the guys out as they walk by, but that's really not what it is. That's a classic, that's a just dad joke through and through. Okay? A manometer, a manometer is really how we pronounce it. It measures the vapor pressure, but it's still going to measure in terms of millimeters of mercury. The reason why I'm doing that is because somebody, how can we measure pressure in millimeters of mercury? What does that mean? I want you to have an understanding of what's going on when we talk about these pressure units. Okay? So these are all the different ways in which we measure pressure. 1 atmosphere will support normal 760 millimeters of mercury. So we're going to use atmospheres, millimeters of mercury, which is exactly the same as a torr. Those are really the two that we're going to use. The kilopascal, that's the actual metric, but very rarely do we use it. Another one that is used is bars, and like with hurricanes. I can't remember what the number is as far as how many bars. I think it has to do with this kilopascals. I think it's 1,013 bars or millibars is the pressure. I'll have to look that one up. But that's when the hurricanes come through, they'll give the pressure of the eye in terms of millibars. That's just another way of measuring pressure.
Why do we need so many different ways to measure pressure?
Because everybody says, hey, I got a different way, it's going to be better. We started with inches, and then when everything converted to metric, that's just the equivalent metric. Then this is just, you know, instead of saying PSI, pounds per square inch, this is newtons per square meter, which is just the metric equivalent of that. So, all right, so we need to know what pressure is, and we need to know how it's measured, and this conversion factors, okay? And again, atmospheres to millimeters of mercury is the most important one that you need to know. But we hear all the time pounds per square inch, so I wanted you to kind of see how impressive that was. Okay, so knowing all of that, let's talk about our gas laws. You guys, this is all going to be a review of Chemistry 1. So, gas laws. First one, Boyle's law. Boyle's law deals with pressure and volume. What's the relationship between the pressure applied on the gas and the volume the gas occupies? As you increase the pressure, what happens to the volume? I heard a mumble. As you increase the pressure, what happens to the volume? Decreases. I think I finally heard that. All right? So what type of relationship is that? Direct or inverse?
Inverse.
Okay. Pressure and volume are inversely proportional. Most of these things are just, we experience them all the time, we know them, but this just puts them into math. Now in math, with terms of x and y, how do you express an inverse proportion? Okay? X is equal to 1 over y, or k over y, a constant, over y, or x times y is equal to some constant k. Now, that's a generic math equation. You learn these in math so you can apply them to a real situation. Okay? Boyle's law is a real situation. So, we say that the pressure times the volume is equal to some constant k. Now, if I increase the pressure, what's going to happen to the volume? It's going to decrease, right, until it still equals the same value for k. That's the whole point. It's going to equal a constant. One goes up, the other goes down proportionally to where they multiply. They're still going to always equal that same number. So I can say then that P1, V1 is going to equal to K, but if I change the pressure to some new P2, and the volume is going to change to some V2, but it's still going to equal K. Right? That's the whole idea of proportion and math. That's why we learn these things in math. Again, I always say math's not a real subject. It's just a tool that scientists created to be able to explain scientific phenomena. Okay? So, I can set these two together and say P1, V1 is going to always equal P2, V2. And that's Boyle's law, mathematically. The pressure and the volume, if you change the pressure, we can calculate what the new volume is going to be, because they're going to always equal the same number. So we already saw that with a balloon. Now, if I decrease the pressure, the volume increased. Kind of a more fun way to do it. Ooh, I made a mess. Where did all that water come from? Something's leaking. Does this thing have a hole in it? Maybe. We'll clean up later. All my stuff, I'm supposed to go to my magic drawer of science and pull out all this stuff. It's all supposed to be there. Well, I'm sure I was gonna look for a marshmallow. It's got a demarsh marshmallow, but we don't have any, so we can. What makes shaving cream creamy?
The shaving.
What makes this foamy?
Probably air.
Trapped air, okay? So if I put this on, oh jeez, there's water everywhere. If I put this on there, and then suck the air out, it just kind of keeps growing and growing. I don't want to go down into the hole. So now when I put the pressure back into it, it just makes a mess.
I mean, it made a mess either way.
Yeah, but I mean the shaving cream just kind of grew because the trapped air just didn't have as much pressure on it, so as the pressure decreased, the volume increased very dramatically. Right? So that's Boyle's law. Charles' law. This is volume and temperature. Volume and temperature. What do we know was the relationship there? If I increase the temperature, what happens to the volume?
Decreases. No.
Increases.
Okay, so what does that mean? Volume and temperature are directly proportional. Now, what must be true about the temperature? What unit must the temperature be in?
Celsius.
No.
Kelvin.
Kelvin. Okay? The Kelvin temperature. So volume and the Kelvin temperature. And Kelvin is going to equal degrees Celsius plus 273. Kelvin plus 273. Now, mathematically, in terms of x and y, how do you represent a direct proportion? Y equals kx, right? So y equals k times x. Or y divided by x is equal to k. So if we do the same thing and say y1 over x1 is equal to k, and y2 over x2 is still going to equal k, because as y gets bigger, x is going to get proportionally bigger at the same amount, so the ratio is always going to be the same. I can say, well, let's just do this. I'm sorry, I should have done it in terms. So we can say v1 over t1 is equal to v2 over t2. That's Charles' law. Now, this is how the Kelvin temperature scale was determined. By the volume. Now, if you try to use Celsius, what happens, according to Mr. Sandlin, if you try to divide by 0? What did he say? So, yeah, something about explodes or you die or what, you know, he just makes some kind of crazy statement about it. Okay? That you can't divide by 0. So you can't use the Celsius. Plus, these guys figured out that the relationship is based on the Kelvin temperature scale, the absolute temperature scale, not the Celsius scale. It only works with Kelvin. All right, so anytime you have T in an equation, it has to be Kelvin. Delta T can be either. But if it's just T, it has to be Kelvin. All right, give me a practical example of increasing the temperature to increase the volume. Boiling well, but again, we're just talking about gases, not changing the liquid to a gas.
15.
Okay? I'm thinking like a hot air balloon.
That works too.
How does a hot air balloon work? Okay,
makes it more buoyant.
okay, because they have the big flame, right? And they pull that thing down, the flame goes, and that heats up the air, so what happens to the volume in the balloon? It expands, so that means it's less dense than the colder air outside of it, and the less dense rises up above the more dense. And so as we increase the temperature, we increase the volume. Okay? Next one is Gay-Lussac's law. Uh-oh.
School's canceled.
COVID is invading the electrical system.
I don't know.
I did hear today, though, that mouthwash with, like Listerine or even swishing your mouth with peroxide greatly reduces, kills the virus.
Drink mouthwash?
Not drinking it, rinsing your mouth.
Wait.
Using mouthwash helps you to prevent.
Until you breathe.
Well, no, because the alcohol inside is going to help kill it. They did a study, virologists did a study saying that it's greatly reduced, but I don't know. Okay, Gay-Lussac, what's left?
I've been saying it, it's working.
What's left?
Pressure and temperature.
Pressure and temperature. What's the relationship? If we increase the temperature, what happens to the pressure? It increases. So what type of relationship? So pressure and temperature, again Kelvin, are directly proportional. So again, we can say that same relationship. So we can say that P1 over T1 is equal to P2 over T2. Now this is the fun one, because if you put an aerosol can into a fire, what's going to happen to it? It blows up, makes a big boom. Okay? If you leave a soda in the trunk of your car in the summertime,
I haven't done that, but let's try it.
okay, it blows up and makes a mess. Because the pressure expands, the gas inside wants to expand, the CO2, and the pressure increases where the can gives way and it makes a mess. Okay? I have this right here. This is measuring the pressure inside this bowl. Basically, what's it saying right here? What's it reading?
14.7.
Well, it is pretty close to, when you look, it's just a little bit less than 15, right?
Yeah.
So it's set pretty close to what we expect atmospheric pressure to be, 14.7. So I put it into boiling water. I heat up the gas inside the little ball. What's happening to the pressure?
It's going down.
It's going up, because as we increase the temperature, the pressure is going to increase. Okay? Now, let's see if I can make this happen. Oh. Sure wish I knew what was leaking. This is really going to make a mess. I guarantee this is going to be a fail. Thank you, I'm here all day. All right, so now I put this into the ice water, and okay, it doesn't overflow.
Ooh. Whoa.
What's happening to it?
Decrease.
It's going to back down, right? Because we're lowering the temperature, and therefore the pressure is being lowered. They're directly proportional. Pressure and temperature. Okay? Lastly, the combined gas law. Mr. Oh,
Oh, I should have said Kobe. Kobe.
You're dishonoring this.
no. Combined. Let's try that again. Third time's a charm. Combined gas law. This guy just went around and he'd like to just put everything together. So he named this law after himself. Not really a person, no. Combined gas law. What if we put all three of these together? What do we get?
Boils, swirls, and
I know, but we're gonna get P1 V1 is Boyles. P1 over T1 V1 over T1 is Charles, and Gay-Lussac is equal to P2 V2 over T2. Now notice in the other three, we always mention 2. We're assuming the third one was kept constant. So if I keep temperature constant, you get Boyle's law. If you keep pressure constant, you get Charles' law. You keep volume constant, like an aerosol can, or like this steel cylinder, ball, keep volume constant, you get Gay-Lussac's law. Always temperature has to be in Kelvin. If you know this one, you know all three. Now you will not be responsible to be able to put name to equation.
Really?
Really.
We have to do that.
I know, but that's a good chemistry 1 thing. We're just gonna learn how to apply them. Okay, when we come in tomorrow, we're gonna really, all of these are nice, but the ideal gas law, P equals nRT, is the one that we're gonna use all the time, but it's derived from this. Have a great rest of your day today.